Hey y'all, good morning. It's Miss Power. I am here doing the review for the Module 3 part of the final review. I don't know what I'm saying. I just woke up. Anyways, we're going to go through the most important key parts of Module 3 that I think you should know for the final. Okay, here we go. Number 1, simplify the following. Final answers should be in radical form. Radical form means that we're looking like this. Right, so let's do part C first. Turns out that part C is just a form switch. We're not actually simplifying or rearranging. We're kind of rearranging. We're not really simplifying anything. We're just rearranging it. We're just saying, oh, this is one way to write it, x to the power of 5/8, right, a fraction in the exponent. And this is another way to write the exact same term, which is x to the 5th, and then we do the 8th root of that. It's the same thing. Right? So this is just a form switch. We shouldn't really have any work. It would be very surprising if we had work here, right? Okay, I'm actually going to do B next and then work up to A. I'm not really sure why I wrote them in this order, but here we are. The big thing to know for part A and part B is that if I have the square root of something and it's squared, whether it's a variable or whether it's a number, or whether it's a collection of both of those things, the square and the square root are inverses. They undo each other. They cancel each other. So x squared and then you take the square root, that's just x, right? 8 squared and then you take the square root, that's just 8. So here, if I see something like x to the 4th, I can think of this as 2x squareds, which means my answer should just be 2 x's. So in the final answer of this problem, I've got an x squared no longer under a square root. We took the square root. That's why it's x squared instead of x4. For the y to the 7th part, we can think of this as kind of 3y squareds plus an extra y, or times an extra y, right? Because there's 7 total, and that's 3 pairs plus 1 kind of hanging out. Which means all of these y squareds underneath the square root get simplified to just y. And this one doesn't get simplified at all. Right, so we'll write that there's 3 y's that come out of the square root and 1 y that hangs back. This is our final answer. So when we're simplifying variables, we're just saying how many pairs are there, that's the number that goes up front. How many leftovers are there, that's the number that goes in back. We do the same thing, let me move these around. We do the same thing for numbers as well, but the kind of trick is we need to put it into a form where it looks like the ones we just did, right? If I say 48, well, there's only one 48. I don't get to cancel the square root in the 48 squared. I guess I'm done. That's not quite it, right? Because what we can do is we can say 48 is the same thing as 24 done twice. And 24 is the same thing as 3 times 8. And 8 is the same thing as 4 times 2. And 4 is the same thing as 2 times 2. And then we get all of these numbers in the back that are basically just going to be our x and y from the previous question, where we consider one of them at a time. And we say, oh, how many pairs of 3's are there? How many pairs of 4's are there? Can we bring any out by canceling these squares? So I've made 48 into 2 to the 4th times 3, which is right, nice. So this now becomes 2 to the 4th, 3 to the 1, j to the 8th. And because we've broken it up into these tiny pieces, now we can do the thing we did for part B, which is collect pairs and bring them out of the square root. So if there's 4 2's, that's 2 pairs of 2. If there's 8 j's, that's 4 pairs of 8. And there's no pairs of 3, so we leave it in the back. We're done. Another way people are doing this is that they notice they do this switch, actually, the form switch, and they say the form switch for the square root of x is x to the power of 1/2. Right, that's a fun fact. And you'll notice that the original exponent divided by half is the ending exponent. This original exponent divided by 2 is 4. 7 divided by 2 is 3, remainder 1. 4 divided by 2 is 2. So we can also just divide the exponents by 2, knowing that we want to do like remainders underneath the square root, and not remainders in front of the square root, or in front of the radical. All right. Simplify the following. All exponents should be positive. This is when we get to use our exponent rules. Our exponent rules say that when we have, let me do it with real numbers. When we have two bases that are taken to an exponent that are the same base, so like x to the power of something times x to the power of something. Let me make this different as well. We have x to the power of something times x to the power of something. We just get to add those two exponents. Because what this is saying is that there's 3 x's being multiplied, and this one's saying there's 5 x's being multiplied. So in total, that's 8. Another rule says that if we were to divide them, we would be subtracting their exponents, because it's saying we have 5 x's on top, 3 x's on bottom, and we can cancel as many as possible, which means we're left with 2, right? Left with 2. If we had 3 on top and 5 on bottom, 3 in the numerator, 5 in the denominator, and we canceled, right, we would still have 2 left over, but the 2 would be left in the denominator. So we'll get there in a second. And then another one is saying if we have an exponent to the power of another exponent, we get to multiply those exponents, right? Because we're saying we've got x multiplied by itself 5 times, but then we're doing that 3 times. That's what the third means, the cubed. All right. So using these rules, w to the 5th to the power of 2 is w to the 10th. W to the negative 6 to the power of 3 is negative 18. And then I get to add those, and I get w to the negative 8. I'm finished. Not quite. Right? I want positive exponents. In calculus, to be honest, we don't really care if they're negative or positive. But it's nice. The reason we're making you do this now in Math 2 is because we really want to hit home that when I have w to the negative 8, instead of saying, oh, let's multiply w 8 times, it means let's divide by w 8 times. Right? So I really want to rewrite this as 1 over w to the 8th, because I want to really, really, really hit home that division is coded by negative exponents. All right, let's do this one 2 ways. First, I'm just going to subtract. I'm going to use this rule over here. I'm just going to say a to the 4th minus a to the 9th is a to the negative 5th. B to the 8th divided by b to the 4th is b to the positive 4. And c to the 2nd divided by c to the 13th is c to the negative 11. Then I say, oh, the b's are being multiplied, the c's and the a's are being divided. I'm done. This is the rule version, right? I said, oh, the rule is when I've got a base over the same base, that's why I did all the a's together, all the b's together, all the c's together, I can just subtract their exponents. The other way we could think about this is just by canceling, right? If I've got 4 a's on top and 9 a's on bottom, and I cancel 4 of them, I'm left over with 5, and they're all on the bottom. For b's, b to the 8th over b to the 4, that's 4 left over, and all of them are on the top. If I wrote out 2 c's on the numerator, and then I wrote out 13 c's in the denominator, and canceled as many as possible, I would be left over with 11 c's in the bottom. So like, there's 2 different ways to think about this. There's probably more ways to think about this, but these are the 2 most common ways to think about this. All right. Determine the classification of, this is the fun one. Determine the classification of the roots of the following quadratics without fully solving them by using the discriminant. Your answer should be one of the following: real or not real. So if I want to know what this instructions are trying to say or are saying, is all of these quadratics have roots, right? We could factor them and set them equal to 0 and find the roots, or we can complete the square and find the roots, or we can use the quadratic formula and find the roots. And some of the questions, namely the one I skipped because it's going to take too much room and I'll do it later, right? This one is going to ask, what are the roots? Like, when you set this equal to 0, what x's give you the right answer? And I want like numbers. I want like 4.9 or something, right? Here, I don't actually want the number. I just want to know, are we going to have i's in our answer? So basically, I'm saying, let's set this equal to 0. Will the answer involve I? That's what this question is asking, right? If you're asking for not real or real, it's on the head. So this one, real means no i's. Not real means there's i's in the answer. We could just solve these. We could literally just complete all the squares, set them equal to 0, solve for x, or use the whole quadratic equation, find the answers, and then look and physically see, does the answer have i's? No, that's a real answer, right? It's too much work, though. It's absolutely too much work. What we're going to do instead is I'm going to zoom in on the part of the quadratic formula that actually tells us whether we're going to get i's or not, right? If we look at the entire quadratic formula, the only place that i's would come from is this part right here, right? Because i's are coded when we see a square root of a negative number. So I want to say, if b squared minus 4 times a times c is smaller than 0, then we will have i's. And that means it's not real. So I only need to plug in b minus 4ac, b squared minus 4ac. I don't need to plug in the rest of the thing. So let's see. B squared minus 4ac is negative 3 squared minus 4 times 9 times 2. Negative 3 squared is 9. 2 times 4 is 8. 8 times 9 is 72. Which means here the discriminant is negative 63. So if I did the quadratic equation, and simplified a bunch of stuff, I would eventually have square root of negative 63, which means I'm definitely getting i's. These answers are not real. Let's try again. If I'm looking at b squared minus 4ac, I'm looking at negative 7 squared minus 4 times 6 times negative 3. Negative 7 squared is 49. Negative 4 times negative 3 is positive 12. Positive 12 times 6 is positive 72. Whatever that adds to, it's definitely positive. That's definitely a positive number, which means maybe it's a gross number, like maybe we don't have perfect square roots. We might, though. No. It's 121, right? It's a perfect square root. It's going to be 11. That's fine. Now I'm curious. Hold on now. This is 80. Yeah, this is going to be perfect square root. But it doesn't matter, right? It's a positive number. So the whole thing is that it's going to be a real answer. There's no i's involved. Last one in this category. If we do b squared minus 4ac, we get negative 10 squared minus 4 times a times c. Already I know it's going to be real because this is going to be a negative times a negative. It's going to be a positive. When we add two positive numbers together, it's going to be positive. Let's do it anyways. Negative 10 squared is 100, and this ends up being plus 40. this is real, is 140 is bigger than 0. Okay. Find the roots to the following equation in vertex form. Okay, so they're saying find x. Find the x's that make this work. They've given it to us in vertex form. So they've already completed the square for us. So for instance, I can take this one and I can add 4 to both sides if I'm trying to solve for x. I can take the square root of both sides. We said that anything squared and then you take the square root, those just cancel out, so this just becomes x minus 5. And then the square root of 4 is 2. The danger zone on these types of problems are that we have to put plus or minus here when we were the ones that wrote in a square root to solve the problem. And that's because if we want x minus 5 squared being 4, 2 squared works, so we can say x minus 5 equals 2. But negative 2 squared also works. It's also positive 4. So we want x minus 5 to have the opportunity to be negative 2 as well. Now I'm going to add 5 to both sides. And now I'm going to actually do this. Now, the first one I'm going to pick plus, the second one I'm going to pick minus. I'm going to say if it's positive 2 plus 5, we get 7 as our root. And if it's negative 2 plus 5, we get 3 as our root. Let's do it again. Over here, the first thing we'll do is we'll subtract 4 from both sides. And now we'll take the square root. X plus 5 squared, square rooted is just x plus 5. Negative 4 squared. There's going to be 3 things going on here. First off, the square root of 4 is 2. That's the first thing going on. Second off, we have to put in the plus or minus because we took the square root. And the third thing going on is that we need an I. The I comes from the negative. The 2 comes from the 4. And the plus or minus comes from the fact that we were the ones that took the square root. Well, we'll practice again over here. Then we subtract 5 from both sides. And we get that our two answers are 2i minus 5 or negative 2i minus 5. Can we simplify any more? No, not really. Right back. We're going to subtract 4 from both sides. We're going to take the square root of both sides. Again, knowing that the square root tells me it's plus or minus, the negative means there's going to be an I, and the square root of 4 is 2. Then I'm going to add 5 to both sides and get that my final two answers are 2i plus 5 and negative 2i plus 5. Okay. Let's simplify stuff, and then we'll get to the bad mamma jamma question, where I think it's going to take up a lot of our time. Okay. Let's start with the second one. What I see here is a bunch of things that can be simplified pretty quickly. We don't have to do this, square root of 48 version where we break everything up, because all of these are already perfect squares. The square root of 36 is 6. The square root of 81 is 9. The square root of 100 is 10. And the square root of 16 is 4. Let's flush this out. This is a plus. We did not do the square root of 9. We did the square root of we didn't do the square root of 81. We did the square root of negative 81, which means we should have an I there. That's a plus. We did the square root of negative 100, so that should be an I. There's a plus. Square root of 16 is just 4. Now we get to say, let's add the 9, or the i's together. And let's add the non-i's together. And we're good. Here, this should remind you again of your Module 1 review packet, where we're simplifying, we're expanding terms and expressions, right? So this is 5 times a bunch of stuff in parentheses, so we just multiply 5 times everything in parentheses. This is -3 times a bunch of stuff in parentheses, so we multiply -3 by everything in the parentheses. And now we collect like terms, right? We've got a couple numbers by themselves. Let's make that 7 look like a 7. And then we've got some i's that can come, some I terms that can combine as well. So 5 minus 18 is -13, and there were i's in the back, so we'll keep the i's in the back. Okay. Now we get to what I think is kind of like the hardest one, because you have to be the most creative. I want to solve one of these using factoring, one of these by completing the square, one of these by using the quadratic formula, and then we'll do the last one just however you like. I'm going to use the quadratic formula twice. I think it's the easiest one, right? The first thing I want to do here is I want to look through this list. I want to pick which one I'm going to factor first. I think factoring is the most restrictive, right? Factoring works on the least or the fewest number of these. So I want to pick the one I want to factor with first. I'm going to pick this one because I think I can do it, right? I think that this is going to be, I don't know. I said it was going to be easy. I think this one's going to be +2 and -15, right? -15 times +2 is -30. -15 plus 2 is -13. The reason I found that one so fast is because I've done this problem 1,000 times. But if we were to slow it down, I would basically just try to factor them all. I'm immediately counting these ones out because they've got 2's in front, and I hate that when I'm factoring. And then I try for this one, and I say, okay, what multiplies to 7? 7 and 1. Does 7 plus 1 equal 5? Oh, no. Right? So then I say, these two are out unless I really need them to work for factoring. And this one's out because I couldn't do it really quickly. And this one's in because I could do it. Okay, we haven't finished this question yet. We're going to come over here. Because not only are they asking us to factor, they're asking us to solve the quadratic. So to find the x's that I can plug in that actually makes this 0. I think the x's that will actually make this 0 are -2 and +15. When I plug in a -2, -2 plus 2 is 0. Nice. And then -2 minus 15 is -17. 0 times -17, 0. Same thing for +15. We just want one of these factors to be 0 because then it eventually will zero out the entire equation. Okay, so I've done my factoring one. Again, I'm doing factoring first because I think it's the hardest, or the most restrictive. The second one I'm going to find is my completing the square. When we complete the square, we're dividing out by the a term, and then we're dividing the b term in half. So if I don't want fractions for completing the square, I want one with a b term that can be divided by 2 and divided by a. So like for instance, this one is not my ideal completing the square one. It works, but it's not my ideal because 5 and if you do 5 divided by 2, you get 2.5, and I don't really love that. Also not my ideal one up here because if you do 11 divided by 2 and then divided by 2 again, because the a term is also 2, I definitely get a fraction or a decimal, and I'm not super enthused about that. So we're gonna let that be a quadratic formula 1. We're gonna let this be a quadratic formula 1. This one I'm gonna use as my completing the square one, right? Because when I divide -4 by 2, just in general, I get -2. And then when I divide it by a, which is -2 again, I get -1. Not a fraction, not a decimal. Ba-da-ba-ba-ba. That's the I'm loving it joke. I don't know if that's what McDonald's commercials sounded like for y'all, because you're younger than I am. I guess I'll ask in class. Okay, we are now solving this by completing the square. Let's do it. The first thing I'm going to do is divide everything by 2. Absolutely everything by 2. Great. Oh, funny. I've been making this harder than it should be for people I've been helping in class. Because it's set equal to 0, we can literally just divide this by 2, right? And not keep track of the 2. The reason we usually can't do that is because we're not doing something to both sides of the equation, so you have to keep track. You have to say, hey, my original actually 2 times as big. But because it's set equal to 0, we actually don't have to do that. Let's literally just divide this by 2. All right, new problem, right? Oh, we could have done that up here too. But it still wouldn't have factored nicely because of this decimal. That's it. Okay, now to complete the square, I divide this by 2. Negative 2 divided by 2 is negative 1. And that's when I say, like, oh, let's put all of these things into a box. I have negative x here, I have negative x here. When I complete the square, I say, oh, the perfect thing to go here would have been positive 1. But the perfect thing is not what we're working with. What we're working with is I actually want this to be negative 1. So I would say to get from my ideal to what I actually want, right, I would subtract by negative 2.5. Go down negative 2.5. Or go down 2.5. So now my equation looks like this. And now this becomes a problem like we did over here. Find the roots in the following vertex form. We've got vertex form now, and now we need to solve for x. I'm going to do this by adding 2.5 on both sides. I'm going to do this by taking the square root of both sides. This is plus or minus. Is that true? That's not true. I'm going to take the square root. 2.5 square root. Oh, geez, it's awful. Right, and then I'm going to add 1 to both sides and get that my x's are either plus or minus 1.58 plus 1. So positive 1.58 plus 1 is 2.58, and negative 1.58 plus 1 is negative 0.58. So I think these are my answers. Did I tell you to leave it in root form? Nope, I think we're just good. Great. Okay. And now, by using the quadratic formula, I want to do both of these. I'll do them kind of like this. The quadratic formula, I'll have it on the board during finals, is x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 over a. Oops. So to set this one up, we get x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. I'll do this for a second. And then when we simplify these, we just kind of like rewrite it and go over it with a fine-tooth comb, and every time just simplify a little more. So I'm going to do all of the multiplication. 121 minus 4 times 2 is 8. 8 times 15 is 120. Is that true? It's true. and 2 times 2 is 4. Now I'm going to do all the subtraction under the square root. Now I'm going to actually do this root. Square root of 1 is 1. And now I'm going to break it up into 2 pieces. Now I'm going to say it's negative 11 plus 1 over 4, or it's negative 11 minus 1 over 4. We'll keep going. Negative 11 plus 1 is negative 10. Negative 11 minus 1 is negative 12. Negative 10 over 4 is the same as negative 2.5. And negative 12 over 4 is negative 3. That's the worst curly brace I've ever seen. Zero. Let's do it again. So now if we're doing this version, we've got x is equal to negative b plus or minus the square root b squared. I just do the squared when I'm writing it. That's a personal preference. You don't have to. B squared minus 4 times a times c all over 2 times a, because our a is 1 here. We go down and simplify, do all the multiplication. This is 28. This is 2. Keep going, do the subtraction. Negative 5 plus or minus the square root of negative 3 over 2. Keep going, do the square root. Okay, here the square root's a little bit silly. Because A, it's negative, and then B, the square root of 3 means nothing. Or not means nothing, but can't simplify any. Is already simplified. Means nothing. It means a lot. The square root of 3 is already simplified, right? The square root of 3 is not a perfect square, so we can't just make it a number without a root, and we can't break up 3 into anything else and try to do the simplifying radicals thing. So the only way we can simplify the square root of negative 3 is to say it's I times the square root of 3. And then this actually makes our lives easier because it means that our 2 answers are this if we chose it to be positive, and this if we chose it to be negative. Choosing this plus or minus to be positive. Can we simplify anymore? Not really. You know, if you really wanted to, you're allowed to say that this is negative 5 halves plus like square root of 3 over 2i versus negative 5 halves minus square root of 3 over 2i. But like these are so like just style preferences rather than like actually we're simplifying things. So I'm happy with the fraction version. Yeah, that's the Module 3 review. I'll go ahead and post that on Google Classroom and do the 4th one.